Welcome everyone, and thank you for taking the time to join us for this webinar session today. My name is Katharina and I will be moderating today's webinar with the subject New Energy Vehicles, Trends, Challenges and Opportunities for the Plating Industry. First and foremost, I would like to introduce to you Dr. Matthias Hoch, who is our speaker and subject expert today. Dr. Matthias Hoch holds a PhD in chemistry and has more than 25 years of experience in the industry. In 2011, he joined the Autotech corrosion protection team as a global business development manager and special projects, focusing on worldwide customer and business partner projects. Dr. Hoch's extensive experience ranges from in-depth market knowledge, product, key account, and project management to business development. Welcome, Matthias. A couple of words I would like to say before we start with the webinar. So the webinar will be divided into two major parts. We have a 45-minute presentation, and then afterwards we have 10 minutes time for a Q&A session. I encourage you to raise questions during the presentation, and therefore you can use the Q&A function, which you can find on the top right corner of your screen. Keeping confidentiality, we will not publish the questions, so you can only see the question which you have posted yourself into the section. We will try to cover as many questions as possible during the planned Q&A session at the end of the presentation. If the time allows, we will answer all questions right away. Also, Dr. Matthias Hoch will be available after the webinar to reach out to you via email. Last but not least, there will be a recording available after this webinar session, and we will let you know when it is released and send the link via email. So now, let me hand over to Matthias, and please enjoy the session.
Thank you, Katharina, for the introduction. Welcome, ladies and gentlemen. Thank you for joining today's webinar on new energy vehicles, trends, challenges, and opportunities for the plating industry. My name is Matthias Hoch. I'm working in the corrosion protection team at Autotech. In the next approximately 40 minutes, I will present you some trends in the automotive industry, which provide certain chances for the future of the plating industry. As Katharina already mentioned, please post your questions during the presentation so that I can answer as many as possible in the following Q&A session. So let's get started. Here is the agenda for today's webinar. I will start with a short overview of the automotive market development. Then I will dig into some trends of the market, as well as into trends which are directly connected to electrical vehicles. Topics in this section are coefficient of friction, durability, weight reduction, contact corrosion, and electrical conductivity. Last but not least, there will be a short summary. So the global automotive production world market. This slide here shows the global production of light vehicles in the years 2016 to 2019. Due to the uncertainties of the COVID-19 pandemic, I have intentionally not provided any figures from 2020 onwards. We'll certainly see a significant downward trend this year, but I'm very sure there will be a steep increase once the pandemic ends. And of course, the restart will be from a much lower level than today, but the climb of the market will be even steeper. What we can see in this graph is that the number of internal combustion engine vehicles, which are the conventional cars using fuel or diesel, is decreasing. These are the red bars in this graph. One cause for the decrease is the overall reduction of car production already in 2019, but it's also an effect of the replacement of the ICEs by electrical vehicles. Those electrical vehicles show a steep increase, and you see this in the two blue bars in the graph. The pure electrical vehicles start from a very low number in 2016, but they improve by 350% in 4 years only. The hybrids already start on a higher number in 2016, which was around a little bit more than 2.5 million cars, to more than 5 million cars in 2019, which represents an increase of approximately 200%. These two numbers in green here in my table highlight the trend in the automotive industry. This slide shows the global production of light vehicles. Here, this slide is a survey of the German market as an example of an important automotive country. It compares the figures from 2012 with a forecast of 2030. In 2012, almost 100% of the cars were common combustion engine cars, whereas this number will decrease significantly in the upcoming years. Of course, the uncertainty in the forecast is very wide, and therefore we see a wide variety in the numbers. You see here 60 to 90% is an estimation for 2030 for the combustion engine cars. But we can estimate approximately 10 to 30% of new energy vehicles in 2030. But at the same time, that means that the majority of cars will still contain a combustion engine. So we have the chances in both markets. Fuel cell vehicles will remain on a very low level for the next years, as you can see here, probably 1% in 2030. Therefore, I will not go into this type of car any further today in this presentation. Here in this table, I summarize the opportunities for the general metal finishing industry in green. In orange, there is a topic which bears opportunities and challenges. And finally, the red issues, they bear risks for our industry. The first green topic we already discussed. It is the global long-term automotive production trend, which is expected to increase after the corona pandemic. The second topic deals with the trend for an increasing share of premium cars. I will talk about this a little bit later in this presentation. The third opportunity is a technology upgrade based on environmental regulations worldwide, for example, REACH, for example, the Chinese environmental storm, but also increased requirements like coefficient of friction. Number 4 on my opportunity list is a technology upgrade in corrosion protection and wear resistance finishes to ensure a longer durability of the cars and fulfill increasing warranty demands, which can already today last up to 7 years. The orange opportunity challenge topic deals with the increase of the new energy vehicle cars, which I personally see more as a chance than as a challenge. Finally, there are 2 red topics which are more a risk than a chance. Firstly, potential alternative technologies can enter the market, replacing electroplating, for example, paint for decorative application or adhesives replacing fasteners. And possible design changes or fashion trends, which can influence the general metal finishing usage, bear also a certain risk. In the rest of this presentation, I will concentrate on the opportunities and the chances for our industry. So here we see the increasing trend of the market share of premium class cars. IHS, they predict a production increase during the next years from 2020 to 2025 of 6.3% year over year. And these premium cars, they have a high value interior and exterior. Therefore, we need high value interior and exterior components. For example, decorative corrosion protection finishes, visible brakes, deep black systems, or brighter wear-resistant coatings. Furthermore, those kind of cars are larger in size. So also the parts are larger in size, which also gives more surface to plate for our industry, which is a big chance. And more valuable materials, for example, for wheels and wiper arms, will be used. And also this gives opportunities for our industry. The pictures on this side were already shown before. But here I'd like to highlight something else. An internal combustion engine car on the left side has much less engine and transmission elements compared to a plug-in hybrid, which is shown on the right side, that offers multiple chances for our industry. For example, a medium-sized internal combustion engine contains approximately 16 kilograms of fasteners, which corresponds to approximately 2,500 pieces. A plug-in hybrid, however, contains approximately 20 kilograms of fasteners, which correspond to approximately 5,500 pieces. So a higher number of parts and consequently a larger surface area, which represents a good business chance for our industry. Of course, many of these parts, especially the screws, are very small, which requires in future a special barrel design with adapted plating parameters. Coming to the topic of coefficient of friction. The coefficient of friction requirements became more and more complicated and difficult during the past years, and this trend will go on for the next years. For example, the industry is asking for stable friction not only against steel, but also against aluminum, E-coat, or powder coat at the same time. Furthermore, there are requirements for fast pre-tightening and slow final tightening. The friction specification limits are pretty tight. Sometimes multiple mounting is required, up to 20 times. And finally, heat loosening must be passed. As an example, I'd like to compare the ISO 16047 from 1991 with the MBN 10544 from 2018. ISO 16047 has pretty simple requirements, whereas the MBN requirements are much more complicated with pre- and final tightening, with multiple mounting, and measurement against steel, against aluminium, and against E-coat. And the big challenge is that everything has to be in a tight range of 0.08 to 0.14. The good answer in this challenge is that this target is achievable for both, for a zinc flake system as well as for a galvanic system. All requirements for steel, for aluminium, and for E-coat are fulfilled as it is indicated in the pictures in the middle of this slide. You can see the successful process sequences on the bottom of this slide. For zinc flake, this is 2 times Syntec 200 plus Syntec Top LV. And for the zinc nickel process, it is CINI AL 450 plus Tridor DB passivate plus Sealer 350 WL8. Longer durability. I already mentioned this as an opportunity. What does it mean? So we need technologies to resist the longer durability of the cars. In this graph, it's shown different regions of the Earth, Japan, USA, Europe, and the average lifetime of cars in years. You can see, for example, in the blue graph that in Japan, the average lifetime of cars in 2006 was 11.1 years. It increased to 2015 to 12.4 years, which is about 10% longer lifetime of the cars, and it's a year-by-year increase of the lifetime of 1.2%. In USA, the lifetime increased from 9.9 years to 11.4 years, which is an average increase year-by-year of 1.8%, and even more drastic in Europe, from 8.4 years in 2007 to 10.7 years in 2015, which is an increase year-by-year of 3.1%. So the lifetime of cars on our streets is increasing steadily. This means also we need higher corrosion protection requirements, and this also indicates an increase of the need for zinc nickel, for sealers, for duplex coatings, for example, electrolytic coatings combined with the top coats from the zinc flake family. Also, increasing requirements for wear resistance become more and more important. An example for longer durability requirements in the future are brake pads, or more specific, the backing plates for brake pads. Today, in a standard combustion engine car, the brake pads are changed every 2 to 3 years, and they are looking like in the picture on the top of this slide. So the pads are worn, and the backside, the backing plates, are rusty. As already mentioned, we expect an increasing number of electrical vehicles in the future. We do not only see this trend, but it is also promoted by numerous governments. I'd like to report on 3 important automotive countries. In China, the NEV subsidies and tax break policies were extended until 2022. The battery charging infrastructure received a higher invest of 2.7 billion yuan, which equals approximately 390 million US dollars. China also wants to increase the share of new energy vehicles in the market to 25% in the next 5 years, coming from 5% only this year. The market share of plug-in vehicles in Germany in the first half year of 2020 was already 7.7%. This number is expected to grow even further in the second half of the year because the government offers attractive incentives and more electrical vehicle models will become available later this year. And finally, in France, President Macron put a goal of 1 million clean cars within 5 years from now. And France wants to become the top producer of these vehicles in Europe. All these measures will increase the market share of new energy vehicles significantly. But what has this to do with backing plates? That's a good question now. So when we look to the braking in electrical vehicles is mainly done with a recuperation system, resulting in less frequent usage of the normal brakes. Consequently, the brake pads are less worn and will last much longer, probably up to a lifetime compared to the 2 to 3 years lifetime today. So probably 10, 11, 12 years in future, and today just 2 to 3 years. Therefore, a high corrosion resistance for the backing plates is absolutely necessary. And the more electrical vehicles are produced, the more of zinc-plated backing plates are needed. In the picture on the top right of this slide, you can see a common backing plate as it is today, which starts corroding already after a short time. That's because today most of the backing plates are just phosphated and/or powder-coated. In order to increase the corrosion resistance, a more sophisticated system is necessary, such as, for example, zinc nickel plus passivate plus sealer or paint. With such a system, the future requirements can be achieved and brake systems can survive the requested very long lifetime, stay attractive over the whole time, and last but not least, and very important, deliver the required safety. Next topic, weight reduction. So on this slide here, I highlighted the range of several battery electric cars. It is very obvious that the high-end electrical vehicles already have a medium range driving distance, but economical electrical vehicles with sometimes only 200 kilometers range, they need a strong improvement. Such an improvement can only be achieved by either more battery power or weight reduction. More battery power is only possible with more battery cells, but there is not enough space in smaller cars. In addition, more battery cells add more weight, which in turn leads to a shorter range. Reducing weight is therefore the key to improving the range of electrical vehicles. In order to reduce weight, new materials are introduced in the automotive production, such as carbon fiber reinforced plastic. I will call this later in my presentation just carbon fiber to make it easier, aluminum or magnesium. With that, challenges are introduced to our industry. One aspect and one challenge is the galvanic or contact corrosion, and another one is the electrical conductivity. So I will first start with the contact corrosion. A few words on the theory first. Galvanic contact corrosion is an electrochemical process in which one metal corrodes when it is in electrical contact with another one in the presence of an electrolyte. Important for the estimation of the contact corrosion is the electrochemical series, which is shown on this slide on the right side. The elements or substances on the higher end, on the positive side, are more noble and therefore corrosion resistant. So this is, for example, you see here, gold or titanium. The elements or substances close to the bottom are less noble and therefore prone to corrosion. The important thing is the potential difference between two elements. The smaller the potential difference, the lower is the risk for corrosion. The larger the potential difference, the bigger is the risk for corrosion. So for example, when you bring gold in contact with magnesium, then the magnesium will corrode very, very fast because we have a very, very big potential difference. The first lightweight material I want to highlight is carbon fiber. As you can see, carbon fiber is pretty high in the electrochemical series. So it's here on the top of this electrochemical series. The elements or substances on the, it is therefore other substances which are in contact with carbon fiber, like iron, zinc, or zinc nickel, are prone to corrode. There are several options to protect the screws from corrosion. It is possible to put a plastic cap on the screw to avoid contact to the carbon and stop the electron flow. Or we can use titanium, which is on a similar electrochemical potential as the carbon fiber, as you can also see in the electrochemical series. These two options require space and are expensive. Another possibility is a so-called CP combination. a combination of galvanic zinc or zinc nickel plus a passivate, and additionally protected by a thick top coat as a kind of isolation layer. Some examples of our investigations are shown in the next slides. In our tech center trials, we used epoxy-embedded carbon fiber boards, in which we placed screws plated with zinc and zinc nickel, coated with zinc flakes, and additionally with different CP combinations. We did silver coatings, which you always see on the left side on my slides, and we did black coatings, which are shown on the right side of the slides. All screws were fixed with plastic nuts, which is seen in the middle, which is called backside. The carbon fiber boards were then put into the neutral salt spray test up to 720 hours. And the results will follow in the next slides. There is another special feature to be mentioned, namely that the plates were scratched before they were fitted with the screws. Why that? As already mentioned, the plates are made of epoxy-embedded carbon, in which the epoxy can act as an insulator. In real life, we all know that when we screw, we destroy at least part of this epoxy insulation and get a direct contact with the carbon. So we forced this contact by scratching the boards to make our test in our tech center more real and closer to real life. The difference between scratched and non-scratched boards can be seen at the bottom of the slide. Screws screwed into non-scratched panels benefit from the insulation of the epoxy and show almost no corrosion, which is here after 240 hours salt spray, while those in scratched panels, those ones here, already corroded considerably. Up to 120 hours, the results you see here. So we got in the neutral salt spray test acceptable results with zinc, zinc nickel, and some zinc flake systems with dedicated process selections. Not everything was good, but there are still some good systems, either in silver and in black coatings. But we also observed systems which already got severe corrosion, white corrosion as well as red corrosion, especially on the right bottom picture. Finally, after 720 hours, all systems in our test showed red corrosion. Even the zinc nickel parts and those plated with a CP combination showed severe red corrosion. To make this degree of severity clearer, we also inserted screws into the neutral salt spray test that were plated along with those in the aforementioned tests. So they came out of the same barrel. But these screws on this slide here, we did not bring into contact with carbon fiber. We don't see any red corrosion here, even after 720 hours, which makes the strong contact corrosion problem with carbon fiber even clearer. So those screws here, which you see now, came from the same barrel than those ones. Those ones were not in contact with carbon fiber. Those ones were in contact with carbon fiber. So to summarize our preliminary findings for contact corrosion with carbon fiber enhances the contact corrosion to all kind of coated iron screws significantly. If the carbon fiber surface is still intact, so when the epoxy is not scratched or not defected, then we get acceptable neutral salt spray results with all kind of surface coatings. With the scratching up to 100 hours in neutral salt spray test, acceptable results can be achieved with either zinc, zinc nickel, or zinc flake systems with dedicated process selections, not with all, but with some. But after 720 hours, all samples show red corrosion, with zinc being the worst and zinc nickel being much better. So the outlook on this topic, we will do more trials here with more sophisticated coating processes, especially looking into the CP combination systems to improve corrosion resistance against carbon fiber. The next contact corrosion test we did is with aluminium. So we had aluminium panels and screwed in plated screws. So we had one blind reference, which you see on the left side. This is with plastic screws. So here, no galvanic corrosion can occur. And on the right side, you see the aluminium panel, which was where the plated screws were put on, where we expect the contact corrosion. All screws, again, were fixed by plastic fastener, plastic nuts on the backside. In this slide, we see the results already after 720 hours in salt spray test. The blind reference is shown in the middle of the page. Zinc plating with organic top coat can survive these conditions, whereas zinc plus inorganic top coat shows severe red corrosion. So this is on the left side of the slide. The same for zinc flakes. Organic top coats show positive results. Inorganic top coats fail, which is probably hard to see here on this picture. I put a non-OK here. You see some red corrosion at the borders of the screws. Zinc nickel shows by far the best results with all plating sequences. After 1080 hours and under head evaluation, the result is even more clear. Zinc flake systems with organic top coats and in particularly zinc nickel platings can pass the test. The clear recommendation for parts that come into contact with aluminium are therefore zinc nickel plated parts. So to summarize aluminium, the low potential difference between zinc nickel layer and aluminum base material reduces the current and slows down galvanic corrosion of assembled components. In agreement to the electrochemical potential difference, zinc nickel plated screws show much less corrosion than zinc plated screws. Again, we have this green arrow here, which is a short potential difference between the zinc nickel and the aluminum. Therefore, we get low corrosion, whereas the red arrow is a bigger potential difference between zinc and aluminum, and we get more corrosion. Standard zinc plated screws and zinc flake systems with an inorganic top coat, they can pass 480 hours, but they already fail after 720 hours. A so-called CP combination, so a combination of galvanic zinc process with an organic top coat, can even pass 720 hours. Zinc flakes with organic top coat pass 720 and even 1080 hours. And by far the best is a zinc nickel system. All zinc nickel systems passed 1080 hours. Then the last is the contact corrosion to magnesium. You see magnesium is on the very low end of our electrochemical series. So here we expect the corrosion of the magnesium and not of the screws, because all screws are plated with zinc or zinc nickel. And so those screws will resist the corrosion, but the magnesium will corrode. What we did is we had magnesium plates shown here. They were mounted onto plastic cubes, and the blind reference was mounted with plastic screws. Then we had zinc plated screws, zinc nickel plated screws, zinc flake systems, as well as the corrosion protect, the CP combination systems, plated screws. And now we had a look how the magnesia plates will develop, how they will corrode. And as well, we measured the plates before the test and after the test to indicate the weight loss, which is an indicator of contact corrosion. So we see on this slide the results after 160 hours in the neutral salt spray test. On the left side, the initial systems, and on the right side, how they look after 168 hours. The blind reference, as expected, almost no corrosion. Of course, we have a little bit of discoloration of the magnesia plates, but there is no real corrosion. Zinc plated screws, they do not create a lot of corrosion on the magnesia plates. Zinc nickel, you can see very, very severe corrosion of the magnesia. And zinc flake, yeah, it's somewhere in between the zinc and the zinc nickel. And this is also illustrated when we look to the weight difference. So in this table, you see on the left side what was the plating sequence: zinc plus passivate plus sealer, or zinc plus passivate and an inorganic top coat. Then in green, the zinc nickel plated parts, and in gray color, the zinc flake systems. And in the right column, you see the weight difference. So the blind difference had some weight difference, but it's 0.02 grams, so it's nothing. So there was no corrosion. When we look to the zinc plated parts, so we lose approximately 0.1 gram of our magnesium plate. So there is very, very low corrosion. Whereas looking to the zinc nickel, we lose up to 2.6 grams of the magnesia by corrosion. So we get very, very severe corrosion with zinc. And as already mentioned, the zinc flake systems, they are somewhere in between the galvanic zinc and the galvanic zinc nickel systems. So the first choice for fastening magnesium are zinc plated fasteners. To summarize the magnesium, in agreement to the electrochemical potential difference, magnesium shows much less corrosion in contact with zinc compared to zinc nickel, again highlighted by these two arrows here. The potential difference between magnesium and zinc is much lower. Electrolytically applied zinc layers are superior to electroless applied zinc flake coatings. As already seen, zinc nickel is much poorer choice than zinc. And CP combination systems give only minor advantages in this case when in contact with magnesium. And organic top coats seem to perform better than inorganic top coats. And again, the first choice for fastening magnesium are zinc-plated fasteners. Now coming to the electrical conductivity. Beside the contact corrosion, also the electrical conductivity is playing a major role in electrical cars. For conventional bolt connections, the focus is on the correct clamping force to ensure a safe assembly, as already seen in the coefficient of friction chapter. With the increasing need for new components like electrical engines or high voltage storages, new requirements are coming up, such as conductivity, resistivity, isolation, and grounding. The resistance, for example, is determined by numerous different influences and parameters, like the material of the screws and the assembly parts, like the assembling step itself or environmental conditions. We in our industry can only influence the surface treatment itself. And here we found that galvanic zinc coatings show lower resistance than zinc flake coatings. So now already coming to the summary. For sure, the automotive world will change. But don't be afraid, but optimistic. There are a lot of opportunities and chances for the plating industry. New materials will be introduced, and weight reduction, contact corrosion, and conductive coatings will play a more important role than in the past. Apart from that, the corrosion or friction is becoming more and more important and is key to keep the fasteners where they are supposed to be. One high-end solution for future coatings is the combination of galvanic plating with zinc flake layers, which results in highest corrosion protection with excellent visual appearance. Atotech is working very hard to make those systems robust enough to ensure high corrosion performance and the correct coefficient of friction window. With that, I'm coming to an end of my presentation. I hope I could catch your interest and you received some new ideas how to improve plating and secure and increase business in future. I highlighted some of the expected trends in the automotive industry and the related challenges and changes. Due to the time limitation, it wasn't possible to dig deep into all details. So if you have interest in more of the introduced topics, please contact your local Atotech partner who can provide you with more specific information. Now I'm coming to the end. I'd like to thank you for joining this webinar, and I'm looking forward to your questions.
Thank you, Matthias. We will now proceed with our Q&A session. I would like to remind you that we will cover as many questions as possible during our Q&A session, and all the rest will be answered by Dr. Hoch afterwards and after this webinar via email. So I would say let's start. Matthias, I have the first question for you. What is the meaning of CP combination?
Okay, this was probably not explained good enough. CP combination is an expression which we use here in Atotech, and it means a corrosion protection combination. In Atotech, we have two corrosion protection, let's say, lines. So we have the galvanic corrosion protection, the electrolytic zinc and zinc nickel plating plus passivate and a top coat and a small top coat or a sealer. And we have our electroless systems, the zinc flake systems. And in the past, those were two separated systems for itself, and it was not mixed. But now we see big benefits in combining both lines. And so we combine today more and more, and we already have a lot of customers who do this application. So we combine the electrolytical zinc or zinc nickel plating plus a passivate, and then we use one of the top coats out of the zinc flake family and put this on top. These top coats are very resistant against chemical influences, against the environment. They are very corrosion protective, and they have a very good visual appearance. They are in total a little bit thicker than a normal sealer, so they give many advantages. For the future, this could be, for example, an insulation advantage, or as I already mentioned, it gives better corrosion protection or visual appearance. And so the CP combination is a combination of both families, the electrolytic galvanic plating and the electroless zinc flake plating.
Great, thank you so much. I think it became more clear now. What is your expectation for the new energy vehicle development after the COVID-19 pandemic?
That's a good question. And if I knew it perfectly, I would become a rich man. But my personal expectation is now the market is down. So there will be a restart, and it will not be a restart coming from the same level or from the same mix we had before the pandemic. So I expect that many people had now enough time to think about what will I do in future. They had enough time to think about this, and they probably already changed now earlier than expected or earlier than they planned to do. They will start with electrical vehicles or at least with plug-in hybrids. So I think the corona pandemic will increase the speed for the development of new energy vehicles. Of course, coming from a lower level, the whole market is down, but the market share of the new energy vehicles will increase faster. And last but not least, also by all the benefits which are given by many governments of the world, especially in Germany. So the people profit when they buy a new energy vehicle. They get certain thousands of euros back from the government. So there will be a higher market share of these vehicles in future.
Thank you very much. There's another question coming in saying, I'm still not clear why you scratched the surface of the carbon fiber boards.
The carbon fiber boards, they are embedded in an epoxy resin. So the inside is the carbon fiber, and then they have an insulation, let's say an insulation layer outside of this board, and this insulation layer will, when we screw in the screws very not very harsh, so very softly, then this insulation layer will not be defected, and we do not get a contact between the carbon fiber and our, let's say, zinc-plated screw. And when we have only the zinc-plated screw in contact with the epoxy resin, then there is no contact corrosion, because it's like you bring it in contact with plastics or whatever, and we do not see any corrosion. But in the real life, all this is done, so the screwing is done by robots, by machines, by strong tools, not very soft. And we know when you then drill in the screws, you will hurt the epoxy layer, and the screws will for sure come into direct contact with the carbon fiber, and only then we get contact corrosion. And in order to simulate this more harsh process in the mass production of an automotive company, we scratched the boards just to get rid of this insulation layer, of this epoxy resin, and to get a direct contact between the zinc-plated screw and the carbon fiber to see the real effect in neutral salt spray test. What is the contact corrosion?
Thank you very much. Let me see. We have another question here. If braking works with recuperation systems in electrical vehicles, why are brakes still necessary at all then?
Yes, this is discussed also in the automotive industry. When you do a very, very normal driving, very carefully, then you probably don't use the brakes at all. You just use them when you come to your home or to your workstation, and you have to stop the car in full. So when you go down from 100 kilometers per hour down to 20 kilometers per hour, this can all be done with this recuperation system with the little engines, but coming down from 20 or 10 to 0, to really 0, to stand still. Therefore, you need a brake. And what is very, very important, you need a good brake and even an oversized brake for emergency brakes. So we cannot avoid the brakes, because we never know if deer or people or children or whatever is running in front of our cars. Then we have to do an emergency braking. And for this emergency braking, we need a very, very good brake, a very, very strong brake. And therefore, it's also so important to think about the brake pads and the backing plates, that they do not corrode, because the brakes are used much less. So if corrosion can develop, then probably the function of the brakes is lower than in a normal system, which is in use all the time. So we have to keep the brakes functioning. So in a new state, let's say in a almost brand new state, and this is only possible when we have non-corrosion in our brakes.
Thank you very much. Let me have a look. There's another one here. Is it possible to plate already finished brake pads or is zinc nickel application an additional production step?
Up to now, to my knowledge of the market, it's an additional production step. So the backing plates are zinc or more. They are usually zinc nickel plated. Then they go to the tier ones or tier twos who apply the PET material. Here in Atotech, we have one project running where we also do this in order to find the best system, which zinc nickel with which passivate is giving the best adhesion to the PET material and so on. But in this project, we also did several trials where we pre-mounted the pads. So the pad material was put onto the pure steel backing plates, and then we put it into the electrolytic plating process with the zinc nickel. And with our system, so I cannot talk for everything, but with the system we tested here, so with zinc nickel and a certain passivate, and with the primer used by our development partner and the pad material used by our development partner, the pre-mounted pads survived the whole plating process. So this can save, of course, one production step in future, yes.
Thank you very much. We have one more, I think a couple of more. After listening to your presentation, what is the best plating solution for the upcoming requirements?
Looking back to the results of our tests, so the best plating solution, when we look to coefficient of friction, all the plating solutions must be dedicated to the requirements. So this is at the end, it's a function of the sealer or the top coat. How is the lubrication in the top coat or in the sealer and so on. So this is depending on if you talk about a coefficient of friction for Volkswagen or for General Motors or for Toyota or for Mercedes-Benz. We cannot say one fit all. No, that's not possible. If we look to the other topics, especially for weight reduction and the new components or the new materials coming into the market, I think I could show very nicely that for magnesium, zinc will be the best choice. Also, zinc plating doesn't give the best corrosion protection, but it's the only plating which gives good or very low contact corrosion to magnesium. For aluminium, it's certainly zinc nickel. For carbon fiber, it's hard to say. Zinc nickel is much better than zinc, but it's still not the optimum. There is strong red corrosion also on zinc nickel systems, and we are working here with our CP combination systems. So zinc nickel plus a passivate plus a very good top coat, which probably has a function as a kind of insulator, so that we get better contact corrosion or less contact corrosion in this system.
Perfect, thank you. Do you see the trend for increasing new energy vehicle market share more as a chance or as a risk for the plating industry?
I personally see it more as a chance. Probably smaller companies which have less R&D and so on, they will disappear because we get more challenges. We get the challenges of the contact corrosion, we get the challenge of the longer durability, we get the challenge of the multiple coefficient of friction requirements. But the companies who deal with this, who have good R&D and application centers and so on, they will find good solutions, and then with all these new challenges, we can increase our business, especially if others will disappear. And as I showed there in for example, plug-in hybrids, there are more parts to plate. They have two transmission systems. They have the normal common internal combustion engine, and they have the electrical engine. So it's 2 engines. So this is double the amount of screws, double the amount of fixings, double the amount of everything. Therefore, I personally see more chances than risks for the future.
Thank you very much. Looking at the time, we are coming now to our last question. Please don't be sad if we didn't ask your question yet. As I said before, after the Q&A session, Dr. Matthias Hoch will have time to answer your questions via email. So the last question, Matthias, already for today. Why is corrosion protection of zinc nickel better than powder coat?
I think this question also goes to the backing plates where I talked about powder coating and zinc nickel. So when I have a steel backing plate which is just powder coated, I do not have any corrosion protection, no sacrificial layer. So when this powder coat, which is a kind of lacquer, as long as this is intact, it will protect the steel backing plate from corrosion. Yes, but as soon as there is a little defect from stone chipping or whatever, a little hole, then we can get water, we can get salt, some environmental contamination get into our system and will corrode the iron. Zinc nickel itself is a sacrificial layer. So when this is in contact with iron, the zinc nickel will be sacrificed before the iron will corrode. So this gives the very high corrosion resistance compared to the powder coating.
Thank you very much. And thank you, everyone. We really appreciate you being here.